All right, so at this point we know how to solve some pretty basic trig equations. What we're going to add on today is the fact that we know how to solve trig equations within this unit circle you see pictured, but we're going to talk about solving them in terms of all solutions, because we know the unit circle is just representing 0 to 2 pi, and these curves, sine, cosine, tangent, all the trig functions, extend beyond just 0 to 2 pi. So we're going to make some connections here, starting with sine and its reciprocal cosecant, but we're going to focus on sine. So a basic trig equation says sine of x equals 1/2, and I want solutions from 0 to 2 pi. So what we've been doing is we've been thinking about the unit circle. Sine are our y values, so I'm going to go on the y-axis up to 1/2, and it's going to give me these two solutions to the left and right there. And those solutions between 0 and 2 pi are pi over 6 and 5 pi over 6. Great. Two solutions within the unit circle. But let's talk about all solutions. So to think about this, we're going to relate it to our graph that we know, y equals sine of x. That's our sine curve. And if we want to know where those outputs get us, again, 1/2, I'm looking on the y-axis. Well, this would be 1/2 here. Every place the curve hits that, and I can see it's happening many times. The two solutions I picked out were between 0 and 2 pi, and those are the two solutions we're looking at. We got pi over 6 over here, and 5 pi over 6. But that's not the only two solutions on the entire curve. There are additional solutions over here, negative angles, and then positive angles greater than 2 pi. So the question is, how do we name all solutions? Well, we think about how far it would take to get to the next solution there. We're not going to physically name every single one, but we're going to show an equation that represents every single solution. That first solution I named is pi over 6. And then I want to think, how far do I go to get to the next solution that corresponds with pi over 6? That corresponding point would be 2 pi over, because the period of a sine curve is 2 pi. But remember, I could go 2 pi over, or I could go 2 pi over again, so 4 pi. I could go 6 pi over, I could go 8 pi. I could go in the negative direction. I could go 2 pi n away from pi over 6, and I will have another solution where n is any integer value, positive or negative. Now, but I kind of ignored, I did not state the other solution within 0 to 2 pi. That's a 5 pi over 6. If you think about 5 pi over 6, to get to the next corresponding value is also going to be 2 pi away. So I'm going to state that as 5 pi over 6 plus, again, 2 pi n, because it's 2 pi away. And that's going to name, again, also the solution over here, because n could be a negative integer. It's hitting every, what I'm labeling as a green point here. And relating one last time back to our unit circle. So focusing again on that 5 pi over 6, that was over here. If I think about getting back to that solution again, you can go around the circle an additional time and meet back at another solution. That is that 2 pi n. All right, so there's how we name all solutions for this equation. Let's check out another connection here. We're going to do cosine and the reciprocal secant, but again, we're going to focus on just cosine here. So our cosine of x is -1. Again, in the unit circle between 0 and 2 pi, we're saying, let's see, cosine is our x values. So -1, that's going to be this solution over here. That is the solution of just pi. Again, let's relate it to our graph that we know. Our cosine curve looks like this. So where cosine of x is -1, this is my -1 on the y-axis. So it's anywhere it hits that. So it's all of these minimums here. Again, I named one solution, that's pi, but see how there are multiple solutions? Those solutions are exactly 2 pi away. So here I would name it as x equals pi plus 2 pi n. And again, relating it back to the unit circle, pi is a solution here. That's the only one in the unit circle. So you have to go 2 pi to get to another solution. So that would be naming all solutions. One more time here, one more connection we're going to make now, this time dealing with tangent and therefore cotangent as well. Again, when we think about the unit circle, we've got tangent of x equals 1. I know that's my favorite angle. That's that pi over 4 here in the middle. And the other solution where tangent is +1 is the opposite side of the circle in the third quadrant. So those solutions are pi over 4 and 5 pi over 4. Now this one's a little different here. We're going to do the same thing compared to our tangent graph, but our tangent graph looks very different than sine and cosine. And if we want to know where tangent of x is 1, we're talking about every place, every one of these curves hits this line I'm drawing here. So it hits here at my pi over 4, the first value I named. It also hits here, and here, and here, and here, and here. So we see it happens much more frequently. And notice how it's on a regular interval for each one. So in this case, we think about how to name all solutions in the most direct way without being like redundant. To do that, I can name this as x equals pi over 4 plus, how far do I have to go to get to the next solution is pi away between every single one. Because the period of a tangent function is pi, we can condense all solutions into this one statement, pi over 4 plus pi n. And that is because our tangent solutions always come on opposite sides of the circle from each other. Pi over 4 is here, 5 pi over 4 is here. They're always going to be exactly opposite the circle from each other, which is pi away. All right, we're going to connect it with a little practice here now. Just running through some of these examples. We'll do a few of these together. So again, we want sine of x equals root 2 over 2. So when we think about our unit circle, sine of x, root 2 over 2, I'm looking up here and over here. And those solutions within the unit circle are pi over 4, and that's going to be 3 pi over 4. But to name all values of x, we're going to name it as pi over 4 plus 2 pi n. And 3 pi over 4 plus 2 pi n. That's how I would name every solution to that first equation. All right, number 2, we're going to fly through again. So I'll add root 3 over and I'll divide by 2 to really quickly get me cosine of x equals root 3 over 2. And then again, I'll think about my unit circle. Where are those solutions? That's going to be these two solutions, specifically pi over 6, 11 pi over 6. And if I want to state those, giving me all solutions, all right, between 0 and 2 pi, I know those, stating all, pi over 6 plus 2 pi n, and 11 pi over 6 plus 2 pi n. So with these, not a whole lot changing. I'm just restating it as that plus 2 pi n when we have cosine and sine. And as you see this third one coming in here, we got tangent, so it's going to be slightly different because the period of our tangent function is different. Add that root 3 over, and I love my tangent tricks. Anytime it's root 3, I know 3 is the denominator. And if it's going to be negative, I know it's going to be second and fourth quadrant. So those solutions, 2 pi over 3, 5 pi over 3. Now, to state that as all possible solutions, I'm going to state 2 pi over 3 plus pi n. And stating that, if you think about adding pi to 2 pi over 3, I would get to my next solution. And I can continue adding pi as many times as I want to state every single one. All right, we're going to level it up a little bit here on this next one. So now what we're looking at here is avoiding what's called redundant answers by condensing. And we did that a little bit with tangent already, but these are just going to be a little trickier. So let's see what we're going to do. All right, I see a cosine squared and a cosine. I'm going to factor cosine out. Factor cosine of x out. And that way I can factor, and I'm going to say, all right, either cosine of x is 0 or 2 cosine x minus 1 equals 0. Okay, I'll have to finish this one out. So this is cosine of x equals 1/2. Cosine of x equals 0. So based on these two possibilities, let's draw a unit circle and draw all of our solutions. First one's cosine of x equals 0. That's going to be up here at pi over 2. Down here at 3 pi over 2. And then cosine's 1/2. That's going to get me these two solutions of pi over 3, 5 pi over 3. All right, now your first thought would be, okay, I got 4 solutions from these, like 2 potential ways to get my answers. So I would put plus 2 pi n on all of them. You could do that, but that would be what's called like redundant. I can condense my solutions and make it easier to state. Now, the way that I can condense them is focusing in on this first group of answers, these two. So you see how those two solutions, kind of like our tangent graph, are pi away from each other? So I can state those as pi over 2 plus, instead of the 2 pi n, I'm just going to do pi n. So what that's doing is that's stating these two solutions. Now I just need to state the other, the pi over 3 and the 5 pi over 3. There's no good pattern between the two of those. There's no equal distribution as I go around the circle. So those will have to be 2 additional statements. So the difference here is that I could state those first 2 condensed into one. The second ones I can't. So the first 2 I wrote as plus pi n, and then the last couple are 2 pi n. All right, again, let's do tangent. We got a tangent equation, so I know I got to be aware of the period of it. I will add 3 over and divide by 3 to get tangent squared of x equals 1. And then I take the square root of both sides, and be careful. If you take the square root of something, you have to include the positive and negative possible solutions there. So tangent of x equals plus or minus 1. And now I'm going to draw that in my unit circle. Okay. I love where tangent's 1 because it's just right smack in the middle of each quadrant. And since it's plus and minus, I'm hitting every single pi over 4. Okay, so within the unit circle, there's my 4 solutions. Cool. How can I name them in the most direct route that's not going to be redundant? It's not going to be, I can condense it, keep it as simple as possible. And the way that I can do that, if you think about pi over 4 and the pattern happening here, since they're all evenly distributed, I got to think, how far do I have to go from pi over 4 to get to 3 pi over 4? And then to get to 5 pi over 4, then 7 pi over 4, then back around. At any one of those angles, if you add pi over 2, you get to another solution. So stating every possible solution would be just pi over 4 plus pi over 2 n. And that is naming all values of x. All right. We are going to skip by this one. And instead, here's practice for you. So you have 4 problems here to try out. So what you're going to do is you're going to pause this video. You're going to work this out on your own. Once you hit play, I'm going to go to a solutions page where you can check them out. But go ahead and hit pause right now. Write out these questions and answers. And hopefully you tried it out. Your solutions should look something like this. So you'll see in red the solutions between 0 and 2 pi. Then in blue, what's called all solutions. So naming all solutions. And number 3 here has a bit of a special bit of way you can condense these all solutions. It's a little trickier, but you see the pattern. All right, thank you guys. Good job.